Okay, testing. Testing, testing. Got the audio issue solved. A couple minutes yet before we get started here. Welcome to all the attendees. Just doing a quick audio check. Can you type in the chat if you can hear me okay? Thanks for joining us. If you are watching online, can you type in the chat to confirm that you can hear us okay? Sorry about that. I'm not sure why the chat is disabled. So I guess, okay, thanks for letting me know that the chat is disabled. Yes, feel free to use the Q&A. I'm not sure why the chat is disabled, but that's something I'll hope to change for next time. Thank you for letting me know. A little intro and over to you. All right, everyone. Welcome both in the room here and online to the fall 22 installment of our Sustainable Energy Seminar Series. If this is your first time joining us in person or online, my name is Scott Williams. I'm the Research and Education Coordinator of the Wisconsin Energy Institute. And we hold these Sustainable Energy Seminars every other week here at the Wisconsin Energy Institute and online to share the many different ways that experts here on campus are thinking about energy challenges and developing solutions. We'll hear from a number of different faculty researchers here on campus, from both the science and engineering side of things to the social sciences and humanities, to get a more kind of comprehensive look at these different sustainable energy challenges and solutions. This seminar is open to the public. It is also a course for students who are in the Sustainable Systems Engineering Master's Program, as well as the undergraduate certificate in Engineering for Energy Sustainability. As you notice, we have this in a hybrid format, so we do have some folks live in the room, as well as live joining online. Unfortunately, the chat is disabled, but if you do have a question or an issue, please type in the Q&A, and we'll do our best to respond to your question. I'll also turn on live captioning for those who might need it. And I'll disable it here on the screen. So if anyone needs the live transcript, they can click on the live transcript button in Zoom. With that, I'll turn it over to our presenter today, John Berry. He's a professor in the Department of Chemistry here at UW-Madison. His research group broad interests involve structure and bonding in transition metal compounds. And according to the bio on his website, the scientific approach of his research group is to discover new chemistry by systematic investigations of interesting and difficult problems of electronic structure. The reason that we have him here today is to talk about some new research that he and his research group has developed in generating energy from ammonia and the interactions between ammonia and nitrogen. And so he'll talk a little bit about that, as well as more of a broader history of ammonia and its importance to our economy and the future of ammonia, or potential future of ammonia as a carbon-free fuel source. So welcome.
Thanks so much for the introduction and also for the invitation to be here today as part of this seminar series. Hopefully, I'll give you some interesting new things to think about today as we talk about one of my favorite elements, nitrogen, and how we can think about nitrogen in an energy context. And we'll see something about ammonia-powered boats as we get into this. Let's see, does this work? It does. Okay, so I may or may not need to start with this, but our big inspiration is climate change and the idea that we really need to move towards a future that has zero carbon fuels. This is one of the more recent iterations of the information coming from the IPCC. As these warnings get increasingly dire, UN Secretary General is calling this code red for humanity. So in response to this, there have been some initiatives from the White House as well as the Wisconsin Governor's Office that issue executive orders mandating that we try to approach zero carbon by 2050. By 2050, because that's far enough into the future that the White House and the governors are going to be out of office, and so they don't really have to deal with this. But it's close enough that people like me, scientists, can really take inspiration from this and start thinking about what it really means to go to zero carbon. And it's actually pretty stark if you think about it. If you want to try to create a world where we don't have any reliance on coal, oil, and natural gas, that means coal-fired power plants have to go. The petrochemical industry has to go. A lot of my colleagues in chemistry would not be too thrilled about this, but you know, it's something we have to think about as reality. Fossil fuels that we use to get around gasoline, diesel, jet fuel, we have to find other ways of obtaining the benefits that we get from all of these different areas that don't rely on carbon. And that's actually a real challenge for chemists. And I see these as not necessarily bad news for chemists, but good news for chemists, as there are new opportunities to think about how to generate energy using elements other than carbon. And the good news is, you take a look at the periodic table, there's 118 elements. We don't have to rely on carbon. There are other elements that you can think about as a means for creating an energy economy. And what I'm going to focus on today is our interest in this particular element here, nitrogen, which is right next to carbon and has some interesting benefits that I think are worth considering from an energy perspective. So one is that nitrogen is very well distributed about the Earth. It makes up 80% of the Earth's atmosphere. So if you think about this nitrogen as being your source for creating energy, it eliminates some of the problems that we have with fossil fuels that they're localized in specific places that cause geopolitical issues. Nitrogen wouldn't have that problem because it's everywhere. Nitrogen is, itself though, a pretty unreactive molecule. It doesn't even really like to interact with itself, it has a really low boiling point, which means the molecules don't really like to interact with each other, and it's very easy to get them to become a gas. But there are ways to take elemental nitrogen and do something useful with it. Biology has figured this out. It is somewhat of a miracle, though. How do we take this really unreactive molecule and incorporate it into biological systems where it's very heavily used? Every protein has hundreds, if not thousands, of nitrogen atoms in it. DNA, same thing. What is this miracle that causes nitrogen to be incorporated into the biosphere? There are a couple of ways that this happens. There is natural nitrogen fixation. Every time you see a bolt of lightning, what you see is nitrogen being excited to its photoluminescent state, and the color that you see is associated with emission from nitrogen. So every time I see lightning strike, I think of nitrogen. And the other thing that happens when you have a bolt of lightning is nitrogen becomes very reactive in that excited state. So it can actually interact with oxygen through the electrical discharge that occurs there. And you can make nitrogen oxides, which will come down to us as acid rain. And this is one of the ways in which nitrogen gets incorporated into the biosphere, because this is a soluble molecule. It can be incorporated into living systems. Nature has figured out also a more complicated way to get nitrogen into the biosphere, which is through proteins called nitrogenases, which are very large and complicated looking, and they contain a whole bunch of metal atoms. And the metal atoms are what are the places where the nitrogen actually interacts. You split the nitrogen-nitrogen bond, and you take that nitrogen, you add electrons and protons to it until you make ammonium ion, another soluble source of nitrogen that can be incorporated into living systems. And this is one of the metal clusters that is most important in the reduction of nitrogen to ammonia or ammonium. It contains a molybdenum atom, it contains a bunch of iron atoms, a bunch of sulfur atoms, there's a carbon atom in the middle. And so this crazy compound, somehow nitrogen interacts with it and turns into ammonia. We're still trying to figure out how this process works. So there's a lot of questions in biology about how nitrogen gets in there from the exact chemical mechanism. And I wanted to start also with the Industrial Revolution, because one of the most important advances that was made in the early 1900s was an industrial version of nitrogen fixation. And this is kind of amazing. This is from discovery to implementation, a span of only 5 years. It was discovered that you could take a metal catalyst and take nitrogen and hydrogen and transform them in an equilibrium process to ammonia. So the chemical discovery was from Fritz Haber's group, and then Carl Bosch at BASF figured out how to make this industrially viable, and they started making ammonia. This is a process that we still rely on to make a huge amount of the ammonia that is produced. About 180 megatons per year of ammonia is produced through the Haber-Bosch process today, which is absolutely staggering when you think about it. It's not as staggering as the amount of petroleum we use, but it's getting up there. So I want to talk a little bit about this process. It starts with nitrogen and hydrogen. It's a catalyzed process, which means that there's a metal catalyst involved. The metals that are used to do this reaction, the one you've probably heard of is iron. And then there are some more exotic metals that will do this as well. Ruthenium is the best metal for this process. And if you remember the name of this element, we're going to come back to it later towards the end of the talk. This is also importantly an equilibrium process, which means it's a reaction that doesn't go to completion. And because of the fact that it's an equilibrium, you can actually change how much product you get by changing the temperature and pressure. And this is a reaction where it works best at lower temperatures and higher pressures. So there are some kind of demanding conditions in the industrial process that have to be met in order to optimize the yield of ammonia from nitrogen and hydrogen. This is what a Haber-Bosch synthesis plant looks like. The picture from Haldor Topsoe, one of the top ammonia producers in the world. They're a Danish company, Copenhagen. And this is kind of a schematic of how ammonia synthesis works. The inputs, the hydrogen input is actually methane. So the hydrogen here is still derived from fossil fuels. That will become important as we think about how to eliminate carbon from this process. Methane first is reacted with water to make hydrogen at high temperatures, and then this is further reacted to purify this hydrogen. This CO2 that's formed gets eliminated, that would be through this scrubber here. And then basically at the end of this process, you just have a mixture of nitrogen and hydrogen. It goes into the reactor where the equilibrium occurs, where you have nitrogen, hydrogen, and ammonia. The ammonia comes out, gets distilled into the liquid state, cooled down to its boiling point so that you actually make it into a liquid. And then it gets filled into a railroad tanker car. You'll notice that this plant is right next to a railway line, and that's on purpose because this plant will fill up about 50 railway tanker cars of ammonia per day. That's a huge amount of ammonia. So that's how this process works. There have been some Nobel Prizes associated with this for Haber and Bosch themselves, as well as more recently Gerhard Bertel, who is a surface chemist who worked very hard to help us understand the chemical mechanism for how the Haber-Bosch process works, how the nitrogen atoms split from each other and interact with hydrogen to make ammonia. But I'm not going to go into the details of that. I do want to mention that the #1 use of ammonia right now is fertilizer. About 80% of all the ammonia that's synthesized gets converted to fertilizer. And there is another important discovery that was made long ago that helps us with producing fertilizer, specifically ammonium nitrate from ammonia. So typically, if you take ammonia and you just burn it, it'll make nitrogen, mostly nitrogen. There will be some other products as well, but the major product is nitrogen. But it turns out if you want to make nitrate, you have to do something tricky. And this was something discovered by Ostwald a long time ago. This is called the Ostwald process. It's a catalyzed specific oxidation of ammonia. Instead of burning it to make nitrogen, this is a reaction that specifically forms nitric oxide, which is a precursor to nitric acid, and eventually you can react nitric acid with ammonia to make ammonium nitrate. So 80% of the ammonia that we produce goes into making ammonium nitrate. This is used as a fertilizer to grow crops, to feed the world's population. So this is a demonstration of the impact of this. This chart just shows world population, and you can see there's a huge growth that kind of started with the Haber-Bosch process. You can think of Haber-Bosch as the detonator of the population explosion, kind of like that title. It also goes with the next paper, because there's a yin-yang symbol here. There's both good and bad parts about ammonia. There's another explosion that involves ammonium nitrate. If it's not handled correctly, you can have absolutely devastating explosives that make with this compound. So ammonium nitrate gives us life, but it's exceedingly dangerous to handle as well. We have to keep that in mind, thinking about trying to use ammonia for the processes that we want to use it for. And speaking of which, what I'm mainly going to focus on today is the idea of ammonia as an alternative zero carbon liquid fuel. Zero carbon because ammonia, NH3, doesn't have any carbon. Right now, we do synthesize it from a fossil fuel product, but there's the potential for making it without any carbon involved in the process at all. And that's where I'd like to kind of lead us to for this discussion. So this is a chart that just kind of shows a comparison of some of the properties of ammonia versus diesel, propane gas, and bunker fuel, which is the really dirty stuff they use to run container ships. So you can see that ammonia, though it doesn't have as much energy density as these other fossil fuels, in terms of cost per kilowatt hour, it's not that bad when you compare. These are 2020 prices, and these are also volatile numbers. So I wouldn't put too much stock in this. It's a snapshot, but at the same time, it gives you a sense that it's in the right order of magnitude for being competitive with fossil fuels, in particular bunker fuel. With current technology, in principle, what we could do is make ammonia through the Haber-Bosch process. We could take that ammonia, feed it into an internal combustion engine, burn it with oxygen. The process would produce nitrogen and water, and it would be off to the races. And indeed, this sort of process has been implemented before, most notably in the 1940s, in World War II, German-occupied Belgium. There was a blockade against Germany from the Allies. They couldn't get oil from the Middle East, but they discovered the Haber-Bosch process. They had ammonia. So they started feeding ammonia into buses, and they ran a system of buses off of ammonia in the 1940s. More recently, there was a truck built by the University of Michigan that they sent out to San Francisco. Big long trip, 2,400 miles. This one required a mixture of ammonia and gasoline because ammonia, it doesn't burn very hot. So actually a mixture of ammonia and gasoline works better. They did have to stop in Wyoming along the way, but they did make it to San Francisco. I don't know if they made it back. But that at least is proof of principle that you can use an internal combustion engine and run automobiles off of ammonia. And this is an idea that has really taken off in the maritime shipping industry. There have been a number of proposals from different companies to create container ships that run off of ammonia or mixtures of ammonia and liquid propane. So some of these articles say that they plan to have a ship on the water in 2022. I have not found any follow-up articles that that ship is in the water yet. The closest I found is one that says, okay, now it's 2025. But it's in progress. This is something that I think will change a lot the way maritime shipping works. I think it'll have some interesting impacts beyond as the technology gets further developed. So that's one way that we can utilize the current technology and get a little bit of the carbon out of the equation. But as I mentioned, the Haber-Bosch process still does require a carbon-based starting material, methane. So I want to talk a little bit more about Haber-Bosch. Wisconsin is, of course, a major agricultural state. We have lots of agriculture here. Requires ammonia or ammonium nitrate for fertilizer. My question for everyone today, Quiz time. How many Haber-Bosch plants do we have up and running here in the state of Wisconsin? One for A. Okay, two for A, B, 5 to 10, C, D. So most of you have the right idea. There aren't that many. In fact, there are none. The reason for this is the carbon source that we use to make hydrogen, natural gas. We just don't have it here in Wisconsin. So Haber-Bosch plants are localized to places where natural gas is abundant. So major plant in the Gulf Coast, Louisiana. And so what we have is local production, high amounts of production of ammonia, and then a distribution network that brings that ammonia out to where it's needed in the agricultural parts of the US. This is pipelines, this is railway tanker cars, tanker trucks, all of this, which is actually a good piece of news if you think about the idea of using ammonia as a fuel. We already have a really nice distribution setup for transporting ammonia to places in the US where it could be used. So we think about trying to do ammonia synthesis differently to avoid some of the problems of localization and also avoid the fact that we still have a carbon-based source for our hydrogen atoms. Let's think about how this could be done. So here's the Haber-Bosch reaction again. Nitrogen plus hydrogen gives ammonia. And in the ammonia synthesis industry, they talk about different colors of ammonia that have to do with where the hydrogen comes from. In the old days, we used to get hydrogen from coal gasification. This is brown ammonia. And in fact, this is still done in some parts of China. Right now, the most modern Haber-Bosch plants are using natural gas. That's called gray ammonia. And for various ways of trying to think about sequestering the carbon that comes from this, you get these other different colors. But there are other hydrogen sources you can think about. You can get hydrogen from biomass gasification. There isn't a color for this, so I just call it yellow. This corn is yellow. And then what people are calling green ammonia is where you have the hydrogen coming from water electrolysis. This is one that has a huge potential, and this is one that everyone in the ammonia synthesis industry is really thinking about and hoping for, because we have a huge abundance of nitrogen on our planet. We also have a huge abundance of water in our oceans. So this is a way that you could synthesize ammonia that you have very abundant resources, and there's no carbon in this, there's no carbon in this. It's potentially zero carbon. But you still have the Haber-Bosch process itself, which requires high temperatures and pressures, and you'd like to get away from that as well. And so there are also efforts in research to try to think about going beyond the Haber-Bosch process to something that is easier to do and would be even more carbon-free. So one of the ideas is an electrochemical synthesis of ammonia, where you have an electrochemical reaction of nitrogen with protons and electrons at a electrode to make ammonia, and that would be coupled with a water oxidation anode, which oxidizes water to O2. This is something where you would require an electrical input to get this to work, but that, of course, could be done through like solar panels or wind power to create electricity. So it, in principle, could be a zero carbon route to ammonia. And that's something that a lot of different groups are working on, specifically this particular reaction here. Another one that is maybe more more appropriate for here in Wisconsin, where we have a population of 1.3 million dairy cows. You can think of each dairy cow as being a little ammonia synthesis plant, because they produce these cow pies that contain quite a bit of ammonia. And if it's possible to recover the ammonia from this manure, you could make what my students like to call black and white spotted ammonia. This could be used as a power source as well. It would address two problems. One, the new zero carbon fuel, but at the same time, it would give us something to do with some of the stockpiles of manure that we have at some of the larger farms that, if otherwise left as they are, create pretty bad environmental problems. So that's another direction to think about in terms of ammonia synthesis. So what I like to do is replace our current Haber-Bosch process with something that's electrochemical, where the energy input is something renewable, zero carbon, hydroelectric, solar, wind, something like that. You could imagine an electrochemical cell where you have nitrogen reduction to ammonia at one electrode, water oxidation to oxygen at the other electrode, and that would be a way of producing ammonia that does not have any carbon in it. You could feed that into internal combustion engines, but you'd like to improve that technology as well, because as I mentioned, you do produce some of these toxic byproducts when you burn ammonia, and we'd like to avoid that as well. We'd like to replace the internal combustion engine also with an electrochemical way of burning ammonia, because you can control the selectivity of reactions better with an electrochemical cell than you can just by burning something. And so you can think about things called direct ammonia fuel cells that could be used to burn ammonia with oxygen to generate electricity. So ammonia comes in, that gets oxidized at the electrode to nitrogen. Oxygen comes in, gets reduced at an electrode to make water. And I want to tell you a little bit about the progress that's been made with these types of electrodes, and also where my own lab's research comes in this direction. So one of the popular types of ammonia fuel cells that's out there, and these are already out and operating, and I'll show you an example, are solid oxide fuel cells. The idea here is that in the first step, you take ammonia and you heat the bejesus out of it until it decomposes into nitrogen and hydrogen. Then you feed the hydrogen into the fuel cell, and this is just a hydrogen-oxygen fuel cell, which the technology is already well developed. But what this requires is a prerequisite thermal decomposition of ammonia. You could catalyze this and try to operate at lower temperatures, but still, to my mind, it kind of defeats the purpose of using ammonia. You're just using ammonia as like a hydrogen carrier in a way. I told you I'd show you an example. So here's a tractor that runs off of ammonia. This is, I think, somewhere in Vermont, they put this together. So it has a solid oxide fuel cell that does ammonia cracking, as well as it's operating as a hydrogen oxygen fuel cell. And they refuel it with liquid ammonia, similar to gas or diesel refueling. I didn't emphasize this before, but ammonia, it's a gas at room temperature and pressure, but it's very easy to liquefy it and store, just about the same as propane. So you can very easily store and refuel things with ammonia, and this tractor runs that way. So that's one type of fuel cell. Another type of fuel cell that people are interested in are ones where the anode actually has a reaction involving ammonia, where you actually oxidize ammonia at the electrode surface. So rather than decomposing the ammonia first and then oxidizing the hydrogen, you oxidize the ammonia to nitrogen, and then the electrons that you get from that are fed into the fuel cell cathode is oxygen reduction as expected. So there are cells like this. They tend to require pretty aggressive conditions like molten sodium hydroxide, which is not the most exciting solvent I've ever heard of. Higher operating temperatures. There was a new design that came out in 2019 that dealt with some of these problems. They were able to get it down to 80 degrees C operating temperature, aqueous sodium hydroxide rather than melt. But they're still using some electrode materials that are rather expensive, platinum, iridium electrodes. Those are some things that still need improvement. But at any rate, those are the prevailing ideas for this. And I want to give you a sense for what my lab does, because we also contribute to this area. And what we're trying to do is we're making transition metal compounds that will actually catalyze this reaction. So we're not actually working on making new electrodes. We're using very simple, cheap electrodes like carbon-based electrodes, carbon felt, but we're using specially designed molecules that can interact with ammonia, and by undergoing redox reactions at the electrode surface, we can transform ammonia to nitrogen through this transition metal mediation. And this is a little schematic of what the compounds look like that we work on in my lab. So we're coordination chemists. We look at these organic ligands and how they bind to transition metals. And these particular ones are very special because they're designed to hold two metal atoms together in a bimetallic compound. And they're held together in such a way that you can form a metal-metal bond. These metal-metal bonds are a little bit unusual in coordination chemistry. Not a lot of people work on them. So in a way, what we're working on is kind of special in that respect. But they give a lot of really useful properties. I'm not going to go over these in a lot of detail, but I do want to emphasize that because of the fact that you have a metal-metal bond, whatever binds along that metal-metal axis, you can really easily replace that. And that gives a really nice way to think about catalysis, because you want something where you can have something bind to a metal quickly and then release as it gets transformed through the chemical process. So this is in many ways a really nice design for a catalyst structure from the molecular standpoint. And most important for the chemistry that I'm talking about today, these compounds are air stable, they're water stable, they're acid stable, and ammonia stable. That's important. Put a bunch of ammonia in there and your catalyst falls apart and makes ammonia complexes, you're dead in the water. But that doesn't happen in our case. We can do chemical transformations on these compounds where we can actually take compounds like this and replace this good leaving group with an ammonia. And this ammonia complex, which we can get structures of by tying up the hydrogen bonds in structures like this. It's an unstable compound. Very slowly, it starts to eliminate nitrogen and ammonium ion as it forms a reduced form of the complex. So there's a redox event that happens when we add ammonia to this compound. And it's very unusual to have an air-stable compound that you add ammonia to. Ammonia gets oxidized to nitrogen, the compound gets reduced. I don't think I know of any other examples of coordination compound that'll do that. So we were really surprised by that. And we wanted to see if we could take the reduced metal complex and just simply oxidize it back up so that it could interact with another ammonia molecule again. And we can do that in an electrode surface. And so we can demonstrate electrocatalysis with this compound. It oxidizes ammonia to nitrogen again and again and again. at a potential of 0.25, minus 0.25 volts, which is the lowest potential that's been recorded for this kind of catalysis. There were a couple of other reports of monoruthenium compounds. So this is my favorite metal again, ruthenium. These monoruthenium compounds were reported in 2019 that have operating potentials up here that aren't really compatible with trying to make a fuel cell out of it, because this one, it lies above the potential for oxygen reduction. And basically you wouldn't be able to do this reaction and couple it to an oxygen reduction electrode. But ours falls significantly lower in potential compared to oxygen reduction, which means that the energy difference between here and here, we could get that as electricity if we created a fuel cell with this half reaction and that half reaction. Ideally, you want to get an operating potential way down here. This is the thermodynamic potential for ammonia oxidation. So we still have a ways to go to get something that operates closer to this. But this is much better than the catalysts that have been reported before. And one of the ways that we think, or one of the reasons why we think that it works that way, is because of this interesting metal-metal bond that does to the ammonia that's bound to it.
Clarification.
Yeah, sure.
What do you mean by coordination chemistry?
Coordination chemistry is the chemistry of metal ions in solution with ligands attached, and what's attached to the metal in solution. Yeah, it's a good clarification. Yeah, that's my whole field. So I sometimes forget that not everyone else thinks about coordination chemistry all day. But we call these types of compounds coordination compounds because this is the structure that they exist in solution. Metals arranged in that particular way. So we can do this catalytic oxidation at an electrode, but because of the fact that we have such a low potential and it's lower than the oxygen reduction potential, we thought that maybe we could actually do this chemistry with molecular oxygen as well. And this works. We can take the complex and watch ammonia oxidation occur. When we add ammonia to the compound, the two different oxidation states of the compound, they have very different colors. So we could watch this by simple eyeball spectroscopy, but also by UV-Vis spectroscopy to get quantitative information. So that's what I have here. These are UV-Vis spectra, where you see these giant peaks. The purple starting material, those go away and it turns brown. But when we introduce oxygen into the system, to the brown complex, the purple bands grow in, it turns purple again, and you can react with ammonia again. So this tiny compound is acting like its own little internal combustion engine, taking ammonia, oxidizing it to nitrogen, and reducing oxygen to water. So it's a really cool compound. And so that's kind of the discovery that I wanted to tell you about, that has kind of been highlighted recently and has prompted me to put together this talk about nitrogen. There are, of course, important next steps that we're interested in following up with this chemistry. One is to actually generate a prototype fuel cell. We're collaborating with a group in chemical engineering to do this. And we're also looking at trying to make new types of catalysts where we can get this operating potential closer to the thermodynamic potential for nitrogen reduction. I think I mentioned this, but the energy difference between here and here, that's how much energy you can get out of the fuel cell. So if we can make this, get this further down here, we'd really like to be able to get this much more energy out of the fuel cell that we create. So that's more or less my view of how we could potentially move away from carbon to a different element, specifically nitrogen, to try to solve not all of these problems, but at least some of them. We could think about cases where tractors that were using gasoline before. Now we can think about powering them with ammonia. Bunker fuel for container ships. The next step would be something like jet fuel. Ammonia has been used as a rocket fuel before. So I don't think these are such crazy ideas. So ammonia is not going to solve all of these problems, but I think it will be a very good solution for some of these problems. With that, I would like to thank the people who've worked on this. This is my most recent group picture. The only person who was involved in this from this picture is this guy, Mike Fineri, and he just recently graduated. He's off to the University of Minnesota for a postdoc. So everyone else in the group is working on something else. Some of them are working on ammonia-related things, but we also work on a bunch of other things as well. This is work that's been funded by the U.S. Department of Energy. I'd like to thank them for their support and you for all your attention, and I'd be happy to answer any questions.
If you're joining us online, you can take your questions in the Q&A, but we'll open it up to the folks in the room here first. Do you have any questions?
Yeah, so I guess my main question is, what's the reason for nitrogen and ammonia not being talked about on like the same level? Is it because the technology is not there yet, or is it because nitrogen isn't as renewable as other energies, and are we going to be using up vast amounts of it to try and accomplish this?
That's a good question. I think for many years, the alternative fuel discussion has just been centered around hydrogen. And in an ideal world, you'd use hydrogen because it has the energy density, but it just comes with so many problems. Storage and how do you make enough hydrogen quickly? That I think it took some time for people to realize that there are other alternatives, and ammonia is one that I think has just, I don't know, for whatever reason, didn't get a lot of attention early on, but is now getting the attention I think it deserves.
Compared to how do hydrogen and nitrogen and ammonia compare in achieving that thermodynamic potential that in a fuel cell? You pointed out that you're maybe half the way there or something like that with this this fuel cell prototype that you're proposing. I'm kind of curious what a typical hydrogen fuel cell accomplishes.
Yeah, that's a good question. I don't know enough about fuel cells to give you direct numbers.
Okay.
But
Just curious.
certainly fuel cells that are working with like platinum electrodes where there's very little over potential, they're going to outperform what we're trying to do for sure. What we're trying to do is, no one's ever done it before.
Sure. No, I'm just kind of curious what you're up against right now.
Yeah. I don't have those numbers.
Kind of mentioned it briefly when you were talking about using this in internal combustion, but we'll still be releasing NOx. And at least in the Midwest, so there's environmental consequences like nitrate aerosols, which are one of the things that is our main aerosol pollution. And also from a climate change perspective, would you change the abundance of nitrous oxide, which is another gas? Are there byproducts that would eventually go into, for example, nitrous oxide?
Yeah, that's a really good question. So the electrochemical process that we've studied, we see no NOx, just nitrogen, which is good news. So the one thing I would be worried about is ammonia getting out of the atmosphere. And that typically, you mentioned, tends to form aerosols. So yeah, if we really wanted to implement something like this on a larger scale, for sure has to be. I'm not proposing that we all of our gas stations filled with ammonia tomorrow. There's got to be a lot more health and safety.
Black and white ammonia would help with that.
It would, because
The ammonia from
the ammonia that's in manure lagoons right now, some of it comes off as ammonia, which makes the aerosols. As you mentioned, there are processes that will oxidize it to, the bad ones into that one I think is like 100 times worse of greenhouse gas than CO2. It sticks around in the atmosphere. So anything we can do to sequester the nitrogen from those manure stockpiles and use it for something that's not just letting it into the atmosphere, good thing in my book.
So have you, in terms of storing it, to avoid the leakage issue, have you considered tying it up and releasing it at the last, make it available for combustion or reaction in some way?
I like that idea. There's a lot of good news about ammonia. One is a tiny, tiny amount. If it leaks, you'll know it because it has a very pungent smell. So leaks are easy to detect. Wouldn't be the case with hydrogen. And you can think about release systems or capture and release systems for ammonia because it has very well-known and reversible acid-base reactivity. So you could change like the pH of a system either electrochemically or chemically some other way to have the ammonia come in and get captured or get it released at just the right time. I think there's a lot of engineering that could be done to utilize that aspect of ammonia.
Or put it inside of some sort of an adsorbent.
Yes.
Capture it in an adsorbent, there are a lot of these things that are being developed now.
Yes, there are. And some are being specifically developed for applications with ammonia. Yes, there's a lot of people thinking about things like that.
Got a couple questions online.
Sure.
So one question from Michaela. I think there's kind of two different parts of this question. One, is there potential for these ammonia cells to be too energy intensive to produce that outweighs the benefits, or possibly creating waste or other end of life issues? I think in the production of the cell itself, is there concern about the environmental impacts?
That's a good question. We would have to think about that. So we're basically using fairly cheap materials. The most unusual material we're using would be like the ruthenium metal. That's an unusual metal. But using it as a catalyst means that you use a small amount of it. So you hope to avoid that being a problem.
And another question from Jim and Frida says, so when you make ammonia from CH4 from methane, where does that carbon go?
CO2. So you produce hydrogen through steam reforming of methane, reaction of water with methane. That gives you 3 equivalents of hydrogen gas plus CO. And the CO is oxidized. A further reaction called the water gas shift reaction, where CO plus water makes hydrogen and CO2.
This is more of a broad question, I guess, but what is the potential of, like the cost potential of this? Does this technology kind of have the chance to dip into somewhere where it could be used in developing countries, or is it going to stay kind of on that higher level where you're gonna have to be industrialized and further probably to use it?
That's a great question. And that's actually one of the things that I found most attractive about thinking about this problem was the idea, our original proposal, we wrote a proposal to do this kind of chemistry, was not making nitrogen from ammonia, but making ammonia from nitrogen in a way that it could be done in a distributed manner. So you don't have to have these localized Haber-Bosch plants producing all the world's ammonia. You could have like a farmer with a solar panel wherever, taking the electricity that's generated there, making their own fertilizer. That was my original dream.
So you think that's like the end goal? I mean, maybe not now with what you're doing, but it could be an end goal at some point.
Absolutely, absolutely. I would love to see some.
The question online, and maybe I'll paraphrase it to. So there's a concern about the energy density of ammonia compared to traditional carbon-based fuels. So even though it might be cheaper or cleaner, that would that take more of that fuel to go the same distance? And there's concerns over just like pump availability. So what do you think would be a way to overcome sort of the energy density and just the lack of fueling infrastructure currently?
Yeah, we have to play this by ear, see how it goes. We can't take all of the gas stations overnight and turn them into ammonia stations. In a way, it's like, how did we get from horses and carriages to gas station city, between cities? It happens, there's going to be some gradualness to it. There's wrong reasons to do it.
Seems like just starting out and shipping too makes sense because you have very specific ports that you're going to operate
Yes.
at, so you don't have to worry about really extensive fuel.
Yeah, exactly. Certainly, one of the reasons why it makes sense in shipping. Other reasons is there's been more regulation of emissions for areas, alternatives.
So I guess it's still very much in development, but I know a lot of people have concerns about sort of the round trip efficiency of hydrogen compared to electric vehicles or batteries. Do you have a sense of that kind of round trip efficiency of this process of ammonia?
There are some articles that go into a lot of detail. The farther you get from chemistry, the less I understand. Sure. But there are some good areas.
How sensitive is your chemistry to the purity of the? For instance, nitrogen, would you have to separate air first before you could feed it into your process?
That's done for the Haber-Bosch process. For us, we're working with anhydrous ammonia, and we do know that you add water, slows down our reaction. It doesn't completely stop. That is an issue. A major issue if you think about things like recovering ammonia from manure. You're going to have it as an aqueous solution. And how you get anhydrous ammonia from an aqueous solution, that's easier to say. Yeah, that's something we'll need to work on.
you so much for your presentation today. It was really Thanks for all of you joining in person online. We'll join again in 2 weeks. We'll have Professor Shirag Gupta from electrical engineering talking about energy conversion devices, especially gallium nitride and these kind of advanced semiconductors and how that can increase the energy efficiency and the stability of our renewable energy grid integration.